maybe the first 40 minutes talk will be just slowly repeat what Yongbing already stated yesterday, but with some conception definitions for field. And you can take a snap if you already know that, and wake up at the last 20 minutes to see the sketch of the proof. Okay, so the target of this talk was 3 types of elliptic orbifold P1. So as you may stay here for the first week in Dimitri's talk about this modular space of M11. And there are 2 special points on this moduli. So it's this point, at E0, and this point, E1728. So these 2 points have special isotropic group, with this one is Z6 and this one is Z4. So our object of this orbifold P1 is, we use this notation curly X, is defined to be a global quotient for some elliptic curve. So E here is and so now we have 3 types here. P333, P442, and P632. So they can be seen as global quotient of elliptic curves. Let me just write down the. So the first one is quotient by E0 modeled by Z3. And second one is E1728 mod Z4. Last one is E0 modeled by Z6. And as a topological space, we can draw the graph here. So there are 3, each one with 3 orbifold points, and the local isotropic group for them Z3, 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 442, and 632. So basically in this talk we're going to study 3 aspects of the Gromov-Witten theory of these 3 cases. So first is we're going to prove this convergence for Gromov-Witten invariants of 3 types of orbicals. And second, we're going to say about this Landau-Ginzburg-Calabi-Yau correspondence in this dimension 1 case. And the last is some beautiful properties of this Gromov-Witten invariant. So it's the modularity of Gromov-Witten invariance of this orbifold. And in this talk, I'm going to basically focus on the second part. And then you will see the relations of this one to the other 2. Okay, so let's start with this framework of Landau-Ginzburg-Calabi-Yau correspondence. So as Yongbing already mentioned yesterday, that this correspondence we are interested for a pair of data, W and G, and where W is a polynomial of n variables which satisfy the following conditions. So the first one is non-degenerate. That means the 0 is an isolated critical point. And the second data is it is quasi-homogeneous. So that means there exists unique rational numbers qi, we call them weights or charges, such that following condition is satisfied. For any lambda is non-zero complex number. And the third condition is the summation of all these weights equals to 1. So this condition we call it Calabi-Yau condition. And it's not necessary for define this FGRW theory, but we need it for this Calabi-Yau LG correspondence. And so this is the first piece of data W. And the second piece is this group G. Symmetric. So this group G can be chosen from this a subgroup generated by a diagonal element and contained in this automorphism group of this W. So where this automorphism group can be seen as a diagonal matrix of complex numbers such that it acts on this polynomial W invariant. So this W lambda 1 x1 xn equals to W x1 through xn. And there is a special element JW. So I just write it here, which equals to the diagonal. We select the entries to be E 2 pi I times this weight qi. Okay. So now we got these two pieces of this data for this correspondence. So let's see one side of this correspondence. Yeah, I know. So first, one side is this Calabi-Yau side. So in this side, we can consider this hypersurface defined by this polynomial. So we denote it xw equals to, which is a hypersurface sit inside the weighted projective space by weights C1 to Cn. So those weights are determined by this weights qi. Equals to Ci divided some d. This d is the common denominator. And so this group G can act on this hypersurface. So if we choose this subgroup generated by JW, then it's acts on XW. And this actually is trivial. But if we choose other group the action is not chewing. So those are actions. And so now we can consider this global quotient from this hypersurface. So let's denote XW. Mod of some group G tilde is Calabi-Yau, possibly orbifold. So here, this G tilde is defined to be the quotient group of G mod by this subgroup JW. And so that the Calabi-Yau condition implies that this quotient space is a Calabi-Yau, possible orbifold. And so one side of this correspondence is to study. So let's denote this special case. Let's give a notation, curly X. And with if we choose some special 3 types of polynomials, we can just identify this quotient to these 3 cases we listed here, and we will see later. And so one side is this. We study this Gromov-Witten theory for this orbifold X. And what does this mean? So first we have this Chen-Yuan cohomology of this orbifold. So this is naively a vector space first, and it's defined by Chen-Yuan cohomology of this orbifold is equals to the cohomology of the corresponding initial orbifold with some twist on the degrees. And so let me give you an example here. So just if this X is P1 333, then this cohomology is generated as a vector space by the following elements. So we have the identity, and I use, okay, so let me denote this point by X, Y, and Z. So delta X1, delta Xi is the cohomology on this fixed point. By this I is a group element on this isotropy group. So we have delta Xi, delta Yi, and delta Zi. And another class P, which is the point divisor class. And I equals to 1 or 2. So as a vector space, this cohomology is of dimension 8. And so now we can go level up from this cohomology to the whole Gromov-Witten theory. So what we care about is those correlators. Gromov-Witten. So in this talk, I will focus on these ancestor correlators, just for technique. And we define this tau L1 alpha 1. We put the insertions and precise classes. And this invariant is defined on the intersection on this modular space of curves with those precise I, Li, are precise class on this modular space of curves. And a linear, multilinear map, lambda g and beta, acts on this alpha I to alpha n. So here, these alpha i's are elements in this Chen-Yuan cohomology, and we can always fix this special base here in this talk. And lambda is a multilinear map from the n copies of Chen-Yuan cohomology and tensor product maps to this cohomology of modular space of curves. And so we can sum over all these correlators to get these potentials and sister potentials. So first, Gromov-Witten potential here is maybe genus G. You sum over all these correlators. And we put a formal variable Q to track this curve class beta, and put some other formal variables by T, J1 to Jn, Ji, Li, to keep track of this precise class and this cohomology class. And we can even sum over all these genus G potentials to get this Gromov-Witten ancestor potential. So we use this notation A equals to take exponential of another formal variable h bar of this FGGW. Which button? Okay, thanks. And so I'm going to introduce one more conception for this on the Gromov-Witten side, which is so we can also think these potentials as of so let's say Gromov-Witten and sister functions with a variable t belongs to this Chen-Yuan cohomology. And we can even write this t, if we fix this base, so this t can be written as t minus 1 times this divisor class p plus other directions, ti, ti. So those ti's are other elements in this space. And we define this potential function, ancestor function, correlator function, with here is just the same, g and beta, as a function on this t. So is you can put this t as an insertion. So this is correlators, and you put k copies of insertions here. You get G n plus k beta, and sum them up by divide k factorial. Okay, so those are what I need for this Fourier series side. And now let's talk about the other side for this correspondence, this Landau-Ginzburg side. So here we have this FJRW theory for this pair of singularities. And this is a formal Gromov-Fulton type theory, very similar to the stuff here. So we also have this, we have a vector space, FJRW vector space, which is defined to be the direct sum of all G invariant part of this relative cohomology on the fixed locus of group element gamma. So we pick a group element gamma, and we consider this C gamma n gamma, which is the fixed locus of this gamma. Remember that this group acts on this Cn, so we got a fixed locus, and this n gamma denoted as the dimension of this fixed locus. So we can consider this relative cohomology on the fixed locus and take G invariant part to collect as our vector space. So, and I will give you an example for this. Oh, this is relative cohomology. So this is like the preimage of relative parts goes to negative infinity. So like if the fixed locus is just a point, then it's just the cohomology of that point. But we still put some twist on this degree so that it's a graded vector space. And one example here is we can consider this Fermat type of cubic polynomial. And now we write down this cohomology, this vector space. So in this talk, I will always consider this group G to be the automorphism group of this W. And in this case, like in this special case, all the fixed point, all the fixed locus are just a point. And so we can just collect all these group elements as representative in this cohomology. So this one is generated by 3 special elements, which is omega square, omega, omega. So these are just 3 special elements. And with this omega equals to e to the 2 pi I multiplied by 3. So this dimension is also easy to see, like has 8. And so similar as what we have in Gromov-Fulton theory, we have in FJRW theory, this higher level invariance is FJRW correlators. So we consider this W structures. So this is also a geometric counting for this W structures, which is WNG is defined to be those a tuple of orbit curve C with orbifold line bundles L1 to Ln. this is orbit curve, and this is orbifold line bundles, which satisfy the following condition. So we have this W is a polynomial, and we can pick each monomial. And so this line bundles and has this variables of this polynomial. So we take this tensor product to get another orbifold line bundle. It's isomorphic to the log canonical bundle on this curve C. Sorry, this is orbit curve C with genus G and n market point, as we put out here for this notation. And also model some equivalent classes. So the counting here is we have a virtual cycle, virtual fundamental class. Sorry. Let me first say that we can forget all these line bundle structures, so we gotta forget format from this modular of W structures to the modular space of curves. And also we can decompose this modular to be decompositions of this gamma, where each gamma is a vector that on each market point we assign a group element in this G to this curve. And so this virtual cycle we denote as WGN vector gamma. So this sits inside this W structures, homology of W structures tensor with the dual space of this FGRW space. So this gamma equals to gamma 1 to gamma n belongs to n copies of G. And so each element corresponding to a vector space here as this relative cohomology. So the cohomology field theory lambda Gn in this FGRW theory is defined to be this virtual cycle intersect with those cohomologies. So that will give a number. This cohomology class with this homology, fixed homology class will give a number. And then this locate as here in this homology of the modular space. And we push forward to the modular space of curves. Take Poincaré and then multiply with this number. And so with these operators, multiple linear maps, we can define similar versions as FGRW ancestor correlators and potentials. So we denote as FG, FGRW. And ancestors. And also we can think about these functions as defined here. Okay, so now we got two pieces of this data, and it's time to state the Rhine's conjecture on the LGCY correspondence. So the first is, as a vector space, this chain-rank cohomology of the orbifold we have is isomorphic to the FGRW vector space. And then level up, which goes to the genus 0 theory. So here there exists a symplectic transformation which is up to analytic continuation. That we denote this transformation as U, send this Lagrangian cone of FGRW theory to the Lagrangian cone of Gromov-Witten theory. So I won't define this, but you can see this naively as this genus 0 matchup. And then we can, so the third one is conjecture for the all genus. So there exists a quantization operator U hat, which send this ancestor of this FGRW theory to the ancestors of the Gromov-Witten theory. Okay, so here, let me tell you some result about this conjecture, as already mentioned in Ryan's talk. So first result is by Chowdhury and Ryan. Says that the, let me denote here, 1, 2, 3. So as you can see, this is level up one by one. So Chowdhury and Ryan proves the first one holds for all possible pair of singularity W and G. And then the second one is also by Chowdhury and Ryan, that the second one holds for W to be quintic polynomial and G to be the group generated by this JW. And the third one is by Chowdhury, Iritani, and Ryan. The second one holds for all possible Fermat type polynomial W, and with this G again restricted to this JW. So now I'm gonna to state this theorem for this talk. So combined with these two papers I've listed there, first one by Krawitz and me, plus Milanov and Ryan, we've proved that this conjecture holds for all general for the following, for the three types of elliptic orbifold P1. So this holds for P1 3, 3, 3. So this is the first example of all genera. And Now I'm going to tell you what is this W and G for the three cases. So we choose this W to be, the first one is Fermat type. So they are all cubic curves as advertised in the beginning of the talk. And we can easily check that this J invariant for these three cubic curves are just 0, 1, 7, 2, 8, and 0. And it's and this automorphism group W exactly to be the first one is a little bit different because there is again a trivial subgroup X, but finally they are just the same as I listed here. Okay, so this is a theorem. And so the proof of this theorem, so both so the first paper dealing with the A side of this, actually this correspondence is stated for both A side here in this picture. But the proof is use this global mirror symmetry procedure. So we have to go to the B side, and the second paper is dealing with this B side. So thank you. So the B side for this theory is we have to introduce this Sato-Gavento theory. So that is equals to say we consider this universal deformations for a parametrized polynomial W transpose sigma, which equals to W transpose plus extra term, which is a marginal direction. So where this W dual is defined, I just give, so this is the Bergholm Hupich-Kravitz dual, and here I just give you one example, like in the first case as it's self mirror, so it's just equals to the first one, and this universal deformation is you can deform this polynomial with extra directions. So where this phi i's are a basis in the Milnor ring of this polynomial W dual W transpose sigma, and so with special phi negative 1 equals to x, y, z. And for this s not equals to 0, it's generically semi-simple. So we can talk about this Sato-Gavento theory for this universal deformations. So that means we can define those genus G Sato-Gavento correlators, and also we can define these ancestor potentials. So here this sigma have to be not equals to cubic sigma now equals to negative 27. And so here is a picture for this proof, as you may already seen several times in this conference. We have, but mine is like a 90-degree rotation for those previous ones. So you got sigma equals to 0 here and sigma equals to infinity here, and you got 3 special points. And so S1 direction is on this sphere. Sometimes it's more convenient to draw this as a line, because I want those extra lines here as the direction of this SIs. And so that means there is a global B model well defined here, and with this special 2 limits here. So the global mirror symmetry says we have this FGRW theory here and Guillemot-Fulton theory here. So this limit will correspond to this sigma equals to 0, which they call Gepner limit. So here is a LG to LG mirror. And here for this point is called the large complex limit. And here is a CY LG. So let's go from here to here. So it's a LG to CY mirror. And so the correspondence is you're starting from this point or this point, and you circle around and got this LG CY correspondence. Okay. So now I'm going to state 5 steps for the proof of this LG-CY correspondence. And also, as I advertised in the beginning of this talk, so we cover 3 aspects of this Guillemot-Fulton theory: the convergence, the LG-CY correspondence, and the modularity. So they all contain in these 5 steps. So the proof. And WG is restricted to just these 3 cases as described. So the first one is by Horowitz and me. Says about this convergence. So on the Guillemot-Fulton side, if we consider this ancestor function, so here is a little bit different as the notes before. We can sum up all these degrees to get this function. And this one is convergent near is P inverse 1 goes to negative infinity, and for other TIs stay around 0. And for the FGRW part, so we use S, and this is convergent near Si equals to 0. So with these 2 convergence theorems, that this potential function is well defined as a power theory for this T or an S. And so the second step, but the story here is that for the Seto-Gavento series, first well defined for semi-simple SIs, but this 2 point we really want is not semi-simple. So there is this extension problems in this series, and the second step is we can have reconstructions for this non-semi-simple points of FGRW theory and Gromov-Witten theory. So that means all this Gromov-Witten all these invariants, Gromov-Witten. Let me just state on the Gromov-Witten side. So all these Gromov-Witten invariants can be reconstructed from very simple and easy to compute ones. So just from this Chen-Ran cohomology, and a special element delta x1, delta y1, delta z1 with just degree 1 for all 3 cases. And actually, this one is very easy to compute. It equals to 1. So that, and I mean, this state for all these ancestors or descendants and up to all genus are just very simply determined by those invariants. And the similar story happens in FGRW theory, but on the other hand, you have to compute a little bit more. So with this reconstruction, we have this, the third step is the 2 mirror theorem holds true. And these 3 steps implies that this extension problem of Seto-Gavento theory for these 3 cases are solid. To the non-semi-simple points. Okay, so let's see the first step. So we already have, like, at this non-semi-simple point, there are 2 mirror theorems. So the last step is from Gepner point to this large complex limit point. So this is proved by Milanov and Ryan that the extended ancestors are related by a symplectic transformation. So you put sigma equals to 0, there's a quantization of symplectic transformation, send it to the, you put sigma equals to infinity. So now at this step, we already solved the second one, the Calabi-Yau, the Ronald-Ginsburg Calabi-Yau correspondence for those cases. So there is an extra bonus in this theory that we can have beautiful properties of these Gromov-Witten invariants. So step 5 is also by Milanov and Ryan. They prove this quasi-modularity property of Seto-Gavento theory. I use this correspondence, it can be easily seen that these quasi-modular properties for Gromov-Witten. Okay, so now in the remaining 10 minutes, I'm gonna to give you a sketch proof for the first step, the conversion. As step 2 is derived similarly from reconstruction and carefully estimation for these correlators. And step 3 is you already have this reconstruction to very simple, easy correlators. And you can just compute both on A side and B side and match them. And the story in the B side is you have to choose this flat coordinate, so that that's for this case is as actually already finished. In the genus 0 case is already finished by Nomi and Yamada in their paper in 1980. So this convergent. So we begin from genus 0 and then genus 1 and all high genus. So in genus 0, we use WDVV and divisor axioms. So WDVV says, so I give you an example to illustrate how this works. So you can have n insertions here, and with 4 more insertions here and here. And use WDVV. This can be right as alpha beta here, and you put all insertions here. Or you can switch 2 of them to get another 2 graph. So you can put A insertions either here or here. And you also have extra terms. I denote I here. So where I is just a linear combinations of correlators, products of correlators with lower degree or lower genus. Oh, sorry, or lower or less insertion. So I forget one step here is in this picture, this degree is D and this degree is 0. And so this is 0D, D0, and 0D. And all these terms are with other terms. So you can choose here, like you choose alpha to be delta y1 and beta to be delta z1. So in this case, on the left-hand side, you got such a correlator, alpha, beta, with n more insertions and turnaround product of this delta x1 and delta x1, which actually is just a delta x2. Genus 0 n plus 3 with D equals to on the right-hand side. So with this choice, these 3 terms all vanish by the turnaround product property. And you just got this term. And so in this special case, so this gives a reconstruction procedure. But this procedure is like very complicated in genus 0 with 3 or 4 insertions. So a lot of argument is dealing with that because we want to have the following estimation of these correlators. So for this degree is bigger than 0, then this correlator, genus 0 m market point with degree D, the absolute value is controlled by d to the n minus 5's power times c to the n plus d minus 4. So here C is a sufficient large constant, which is just depends on market point N. And actually we can fix this by more arguments. It is like in this case it's just a constant. So this is for genus 0. And then in genus 1. So in genus 0 and genus 1, I only discussed about these primary potentials which without a descendant class. So actually we need only to deal with this term and give an estimation for this. So we'll use Getzler's relation. So this is a relation on the modular space on the H4 for M1 4 bar. And we can write this relation with this graphs. So there are 4 market points, and it belongs to H4. So if you have 2 nodes, then this graph will lies on the cycle of the corresponding graph will lies on this H4. And actually there are 4 different genus 1 components, which as this 4 graph show, and plus some genus 0 contributions. And the relation says that there is an equation for this. And so we can integrate a special homology field theory on this relation to get a genus 1 reconstruction for the correlator we want. So we integrate on this relation by this special homology field theory with 4 fixed insertions we choose by delta x2, delta x2, delta y1, and delta z1. So this is just for the P1333 case. And for the other 2 cases, we have to choose other insertions. And if we integrate on those relations, then you can find that by this choice, so this first 3 graph, the integration is 0. And the non-zero genus 1 insertion just happened on this component with 3 market point here and 1 market point here. So this will gives you a reconstruction for this operator. This is D plus 1. And we got this estimation is as follows. So this, as D increases, this absolute value is bounded by D minus 1 times C 2D minus 1. And this C can be choose to the same C here in the genus 0 estimation. So I'm nearly running out of time, and I just write down for the high genus, we use this G reduction says that if you want to integrate MG, the following correlators. Here, this psi is a monomial of psi classes with degree D. Then, by Ionian's result, that this can be reconstructed from the integration on the boundary class of the modular space. And like, it's just luckily, like in our case, we have this degree formula such that you can just finally reconstruct those invariants with genus 0 and genus 1 potential primary correlators we've listed here. So, and you can carefully running an estimation that the correlators you want here G and D is bounded by this formula. Where here this C is only depend on G and N. And use these estimations, we can give these convergence properties of these correlators. I just discuss these correlators as a polynomial of these TIs with I not equals to -1, and on these i's we use these estimations. Okay, so I stop here. Yeah, inductive, because you can reconstruct, but like the hardest part is like in genus 0 for n equals to 3 and 4 with 3 or 4 insertions. That induction is like a little bit complicated than the other cases. So like you have more like